Hello, good morning, everyone. So welcome to today's MIDI Minatech by Giant, where today we'll have Lukasz Borowik talking about atomic force microscopy for electrical characterization. So welcome, Lukasz. The stage is yours. Enjoy the MIDI Minatech.
Thank you, Chair. So today I will talk about atomic force microscopy for electrical characterization. So after introduction, I will show some examples of electrical characterization by atomic force microscopy applied on devices and materials. So atomic force microscopy was invented in 1986, and together with scanning tunneling microscopy is making part of scanning probe microscopy characterization techniques. And besides, one of the inventors of Binning, together with Roher, get the Nobel Prize for scanning tunneling microscopy. So what is the difference between scanning tunneling microscopy and atomic force microscopy? In scanning tunneling microscopy, you have metallized tip and the sample, and we will detect the tunneling current to scan topography. In atomic force microscopy, we'll have cantilever and attached tip, metallized or not, and we'll have detection system by the laser. So laser focalized to the end of the cantilever and reflected to 4-quadrat photodiode. So by this photodiode, we can read the signals from cantilever, for example, deflection of the cantilever or amplitude set point to use the scanner and to scan, for example, topography, etc. But I will talk about this later. But this detection system is making already the difference that in STM, we must have conductive sample. In AFM, we can scan both, so conductive and isolating samples. So the main part of AFM to have local the resolution is the tip with a cantilever. So this part will change quite often because we must adapt the cantilever and the tip to the experiment. For example, for electrical microscopy, we'll use metallized tip. For example, for contact mode, we must use diamonds, very often diamond-coated tip because there is a lot of friction, so to not damage the tip. We can, of course, on the market we have different tips, but we can change using different tips, for example, super sharp tips, the resolution. We can increase sensitivity using different cantilever stiffness. So this, one more time, this part will be changed very often because we must adapt to the sample, to the experiment. And as well, this part will often degrade, so also we must change it. Apart of AFM tips, we have access to different modes. Here, only for topography, we have 3 or 4 modes to scan topography. Here I present first contact mode. So in contact mode, we'll use deflection signal of a so deflection of a cantilever to scan the topography. So to control vertical force, we will need to have information about this deflection signal and use scanner to scan the topography. Another mode which is very often used is intermittent contact mode. So here the cantilever will oscillate and will keep oscillation of this amplitude constant to scan the topography. There is a variant of this mode, which is called peak force tapping. So here also the cantilever will oscillate, but will control the deflection of the cantilever in each oscillation cycle. So here, for example, we have the movement of a tip down and up, and we have deflection of a cantilever, and we can choose a set point to use during the scanning to keep it constant, to control the vertical force, and then to obtain the image of the topography. And the last mode for topography is used in ultra-high vacuum, so non-contact mode. Here we'll keep the distance between tip and the sample. Tip will oscillate and will detect the attractive forces coming from the sample. So for this, we'll keep the resonance frequency shift to detect attractive forces, negative resonance frequency shift to scan the topography. So we can see by this two previous slides that AFM is already a very versatile system. We can have access to different cantilevers, to different tips, to different modes and environments. Here I choose 3 examples to show the different resolution and different environments by AFM, just for topography. So first example is duetting of silicon films, where we can see the micrometric agglomerate. So this was done in intermediate contact mode using ambient AFM. Second example is DNA molecules obtained by AFM in liquid with peak force. And third image is atomic resolution with non-contact AFM in low temperature. So this is silicon 111 reconstruction. So this is just for topography, but by AFM, you can have access to other different parameters. Sorry to overload this slide, but I wanted to show that what it can be done by AFM can be very rich, and not only for topography. So by AFM, we can have access to different properties, for example, mechanical properties. So for example, have information about adhesion or stiffness or frictional force. With some special tips, we can have information about magnetic field. We can also have information about chemical nature of a structure, or have access to a local temperature. Also, as well, we can have information about optical properties, so for example, fluorescence, or use tip-enhanced Raman to have information about chemical structure. And what I will talk today, have information about electrical properties, so have access to current, potential, capacitance, etc. So for what we need the local electrical characterization. So today we can have many examples, but I choose some examples of devices and materials. So first, of course, for small transistors or micro LEDs, but every kind of device where we have the current flow or charge transfer, we need this kind of characterization. I often characterize also nano objects, so for example, nanowires, or bulk materials. So for bulk materials, if you have some also objects or defects which will influence the electrical properties of materials, we need local electrical characterization. So for electrical characterization by AFM, we can still divide it to different modes. So here I just put some of these modes. Some of them I use, and I will talk later, and I show examples with those modes. Of course, as I said before, we must have with this mode metallized tip, or for example, on the market we have great now single crystal diamond tips, dopes, but anyway, tip must be conductive. So still before going to examples, I want to show the AFMs which we have on nano-characterization platform. So actually we have 2 AFMs under ambient pressure, under ambient pressure. So one is placed under air and second under argon in glove box, and 2 systems under UHV. So one is in CEA-Leti and one in IRIC. So now I show several examples of electrical characterization. So I will start with electrical characterization in contact mode. So first example on the right is rather simple. So it's scanning spreading resistance microscopy, where we will apply VDC bias between tip and the surface, and will detect the current passing through the sample and through the tip. And from this information, we will recalculate resistance. So from this experiment, we can already have information linked to the material, but as well to, for example, doping. This kind of characterization by SSRM is quite often compared to scanning capacitance microscopy, which is quite different, because here we'll apply a part of VDC, also VAC bias with high frequency. And we can see on these plots that this variation of VAC will have impact on capacity, which we can detect. So now, if we measure capacity, this capacity will be dependent of level of doping. So we can detect different variation of capacity in the function of level of doping. What's more, we can detect also phase of change of this capacity, and this will have will give us information about type of doping. So this information is we have more information comparing to SSRM, because by SSRM it's difficult to obtain the type of doping. So first example of this comparative measurement by SSRM and SCM is on bipolar transistors. So we have SCM image in the middle. Together with electrical characterization, we of course can have also information about topography with both techniques, so SSRM and SCM. And we can see, for example, in the middle that we can have from SSRM measurements information about doping gradient. So there is a contrast here. And comparing to SCM also, we can have this kind of information about doping gradient. But from SCM, we can have from phase image also information about doping type. So we can see that this kind of characterization already can be applied directly on the device. The next parameter which I often use for characterization is for electrical characterization by AFM is work function. So a work function is a minimum energy needed to remove an electron from a solid to point immediately outside to the solid surface. So in other words, is a difference between Fermi level and vacuum level. The work function is very useful because it's linked to everything what is on the surface, so oxides, contamination, defects, or charges, and is useful for devices because work function conditions the charge transfer between materials. So this work function we can characterize locally by Kelvin probe force microscopy. So in Kelvin probe force microscopy, we apply VDC voltage and VAC voltage between tip and the sample. And VDC voltage is applied in that way that to nullify the electrostatic field between tip and the sample. And when the VDC is applied to nullify this electrostatic field, will be equal to VCPD, which means contact potential difference. And contact potential difference is equal to difference to work function between tip and the sample divided by single charge. So we can see that VCPD is equal to relatively to work function of a sample, because work function of a tip during the scanning should be constant. So VCPD will have information about relative work function of a sample. And here I present two examples. So first on polycrystalline copper, where in topography we can see already the grains. And on the right, we have KPFM signal where crystallographic direction have impact on relative work function. Second example is rather linked to influence of doping. So we have intrinsic nanocrystal deposited on N-type surface. And on the right, we can see the influence on relative work function. So here there is influence of doping, so change in a Fermi level. This kind of techniques has resolution less than 10 nanometers, can have less than 10 nanometers, and sensitivity to potential less than 5 millivolts. So I said that by KPFM, we can have access to relative work function, but it's also possible to measure absolute work function. I will show that this can be very useful in some cases. So how to do it? As we start experiment with KPFM, the work function of a tip is we don't know. However, we can calibrate this work function of a tip with some calibration samples. So for example, here I choose some metals where I know the work function. And through this equation, as we know work function of a sample, we can deduce work function of a tip. And with this system, we can change after the sample and scan, for example, the sample which we don't know the work function. So here is the example of multi-layers with aluminum gallium arsenide and gallium arsenide, where there is the axis where we have directly absolute work function. So why we are doing this? This absolute work function, from this absolute work function measurements, sometimes it's possible to compare with simulations and have access to the surface states. So here is also the example on gallium nitride. So we have topography and contact potential difference, from which we deduce the work function of the sample, and we compare this value to atomistic simulation by density functional theory, where we simulate different cases of surface states listed here and clean sample. And we can see that the work function of a sample has value very close to the clean sample. Why? Because this sample was cleaved under ultra-high vacuum, so we consider this surface as very clean without any surface states, and that's why those values are matching. We have also other examples of contaminated sample on different materials where we can deduce by this kind of comparison the surface states locally. So besides of measuring of measurements of absolute and relative work function can be very useful for the devices where we have transfer of charges. So here I present measurements on two-dimensional gallium selenide, where we can see a topography, of course, and contact potential difference related to work function. And here, a part of measurement of work function is a function of layers, number of layers. We can also have local information around about antiphase boundaries, so we can measure the work function of this antiphase boundary. So this kind of measurement can be useful after if we have devices. So here, gallium selenides have potential applications, for example, of solar cells, light emitters, to compare this value and have this information to analyze the operation of a device. Second example of work function measurements on devices linked to organic photovoltaics. So here we have the junctions of donor acceptor. We have topography, and we can distinguish already on the contact potential difference of those junctions. And we can measure between those work function the difference of work function between donor and acceptor. So also for this organic photovoltaic example, we can after have information to know more about operation of this kind of device. So next parameter, which is also linked with work function, is surface photovoltage. So surface photovoltage is the difference of work function under dark condition and when sample is illuminated. So this kind of parameter is very useful for example, for different applications linked to solar cells or like emitting LEDs, because we can have information from this kind of from this parameter about surface bound bending, which is linked to charges on the surface, or some dynamical processes of charges, for example, recombination of charge or charge trapping. This I will describe a little bit later. But to show the utility of surface potential, I show here the measurement on silicon substrate with different passivations. This was done with purpose of photodetectors application. And we can see here, for example, that when we put the sample under illumination, the contact potential difference, so SPV, is going to negative value. This is already meaning that electrons are going to the interface or to surface. So we can have already this information. After, what we made is measurement of surface photovoltage in the function of laser power for different passivation layer. And by this equation, where is surface photovoltage, intensity, and A and B parameters are fit parameters, we can have information about bound bending and dynamical processes like charge recombination or diffusion length. So about charge recombination, this I will do more of a focus. So charge recombination is the time which spent an electron in a conduction band before falling back to valence band. In other words, is the time during which the charges can be transferred in a material. So this is very important parameter also for solar cell photodetectors, LEDs, and transistors. We can have different types of processes of recombination with different times of recombination. We can also have other dynamical processes, for example, trapping or detrapping of charges. All those processes we can characterize by different methods. There is no one method, but several methods. But we developed KPFM protocol to characterize those processes locally. So first example link to this characterization of these dynamical processes is on gallium nitride based devices. So here we can see already a topography with defects. So these are dislocation pits. And in each pixel of this image, we are doing this kind of spectrum, which is SPV in the function of time. And from this kind of spectrum, we can also discriminate between different processes linked to trapping and detrapping. And as we are doing these spectrums in each pixel of the image, we can compare the influence of defects comparing to the pure surface. Second example is on GaN-based micro-LEDs. And here we are interested if the trapping effect has influence, if border effect have influence of on trapping effect. So here we can see already from surface photovoltage when on the border we have homogeneous signal, and as well by this point we can see the spectrums, and as well the time of the trapping is the same on the border. So we consider that the trapping and detrapping effect is not the border effect is not affected by trapping effect. There are other processes, I will not go to the details today, which influence border effect of LEDs. So this kind of measurements we can see are rather slow time scale. So we have seconds, are very long. At best, we can go to tens of milliseconds because we have limitation of how fast is our KPFM system. However, we developed other KPFM system to have access to much faster processes, which can go with our actual system to hundreds of nanoseconds, which is called POMPROB KPFM. And here we'll illuminate our sample with pulses of light, very short, and as well we will detect the signal, so KPFM, by very short pulses. And as we have this detection by pulses, we can dephase the excitation signal and detection signal, and we can follow the dynamical, very short time dynamical processes. So one example on this is also on photodetector for photodetector application. So here we have silicon passivated with alumina, and we can see the spectrum of various of light, and we have different processes. I will not go to the details, but we can discriminate here that we have a part of trapping and detrapping processes. We have access, for example, to a recombination of on defects. Another example, which is with lateral resolution, is measurements on organic photovoltaic. So here we have donor-acceptor blend. So we can see topography. We have two components of surface photovoltage, as we have junctions on the surface, and we have positive and negative charge transfer. And after, we have dynamical processes associated to each of the photovoltage with nanometric resolution and with time resolution here going to 1 microsecond. And the last example of characterization is for piezoelectric and ferroelectric materials. In piezoelectric materials, we can have direct effects. So when we apply strain to material, the electric field will appear, and we can have also indirect effect. So deformation will appear when electric field is applied. So we'll use this effects for AFM to detect, to characterize piezoelectric materials. Piezoelectric materials can be also ferroelectric. So if we apply polarization, if polarization can be reversed if we apply the electric field. So in this case, we have also ferroelectric materials. So those kind of materials, piezoelectric and ferroelectric, have potential applications to memory sensors or acoustic filters. So this kind of materials we can locally characterize by a piezo-response force microscopy. So this characterization method is in a contact AFM with contact mode, and we will apply VAC bias with some frequency, dependent of mode we apply high or low frequencies, and we'll follow the deformation of material since we are applying electrostatic field. So we can measure this amplitude of vibration of material, and a part of this, we as well can measure the phase shift between excitation and how the material will strain, will expand and strain. So as a result, we'll have delta Z measurements, which is dependent of piezoelectric coefficient, so it's D33, the vertical coefficient, piezoelectric coefficient, and applied voltage, and as well phase, which will be dependent on ferroelectric domains. So here I present an example of this kind of measurement. So we can see first the amplitude, so this is this deformation, phase, and we developed the protocol where we can analyze the size of these domains. So domains polarize up and down, so we can have a ratio between local domains up and down. And for each domain, we can measure the deformation by AFM locally. Okay, so this was last example of electrical characterization. There is a lot of information during this Midi-Minatech about the electrical modes, but what is important to keep in mind that AFM has a tip, and we can have the local information, but it's not only for topography. And there is possibility to use various modes, so access to different parameters, and especially to have local electrical characterization and apply the materials as well to device characterization. So I want to say thank you to Midi-Minatech team for invitation, to AFM group, so Nicolas Chevalier, Denis Mariol, and Benjamin Grevin, and to all my students, so internship students, PhDs, and postdoc, and all my colleagues from PFNC. And be invited to the next Midi-Minatech.
Thank you very much, Lukasz. We can, of course, give an applause to Lukasz for the interesting talk, for this fascinating overview of all the properties and type of measurements that can be accessed with atomic force microscopy. So now the time is the time for questions. You can raise your hand when you have a question. You can ask questions in French as well, so you can choose. We have there the first question already.
Well, thank you. I have a rather long question. Maybe I didn't get what you said. Several times, thrice at least, you mentioned organic structures, DNA or organic structures, whereas most of your lecture was about metals, metallic structures, metallic layers. But in your opinion, how can AFM help characterize organic structures when they work, especially with no-touch cantilever, you know?
With no?
When it doesn't touch
yes.
the sample.
Okay, so no, it's, I think here I did not present only metallic materials. There are semiconductor materials and metallic sample as well, but mainly semiconductor materials, which are conductive. Concerning organic materials, for example, here the aim, okay, first thing, we can do the measurements without touching the structure, because, for example, this kind of measurements were done by non-contact IFM, so tip is not touching at all sample, so it can be it can be done. So after we can, I don't know if I understood your question correctly, but this kind of measurement, so I presented dynamical measurements of dynamical processes or work function linked to surface potential can be after linked to device operation. So for example, we can see if this device is working correctly or not, or some parameters we need, which I was talking about, which we can supposed to have, but finally we measure locally different values. We can after change, for example, the fabrication of these organic materials to take to account this kind of parameters. Okay, so this is the interest of this kind of characterization. And by AFM, you can electrically do the measurements in contact mode, and as well here I'm mainly present in non-contact mode. Okay, both organic and inorganic materials. I did not precise this, but mainly I'm working with non-contact mode here.
Okay, thank you. Other questions, maybe? Yes, please. There. Yeah.
Hello, that's a beginner's question, beginner to AFM. Is the contact mode distracting the sample?
It depends, yes, but yes, you must very often take to account that it can destroy the sample. After, in AFM, the aim is that you must control the vertical force. So how much force you put, if you to not destroy and to destroy less the sample, okay? But with contact mode, yes, you can destroy your sample, especially if you have some fragile materials. You must take to account this. Anyway, if you are doing this kind of measurements, you can directly see this, because you take one image and after another image or larger image, and you can see if your sample surface change or not. Okay, so even if it's it can be destructive, you can follow the change in your surface.
In relation with that, well, we have other questions. When you do contact mode measurements, how you can tell, well, how can you estimate the contact resistance between the tip and your sample? In the example that you put, where you would measure the resistance of your layer by
Yes.
doing a two-point measurement, how you estimate the contact resistance?
The contact resistance, this is spreading resistance. So you must take to account this, but you don't know normally your contact resistance, because there is many factors which will influence this contact resistance. You can have, for example, even some oxides. So you measure the relative value of the resistance, and this relative value is not absolute value, because I think you are asking about absolute value.
Yeah,
okay.
yeah.
Here the aim is to do the images, so you have the resolution, and you compare the fragment of your sample with other. Okay, you have relative change in resistance, but we will not search here the absolute value of resistance. Okay.
Okay, thank you. More questions? Yes, we have here through the chat. Est-il possible dans un système comme gallium arsenide de voir la force d'extraction pour chacun des deux atomes? Okay.
So
is it possible to see the extraction force for both atoms, for gallium and for arsenic?
But then I cannot access. Yes, for sure. I never did this, but for this the main problem is that firstly you must maybe go to atomic resolution to have access to atoms first, and after, if we are talking about single atoms, to calculate this. So it's very difficult to have with electrical characterization such resolution. There are some very low quantity of publication, but number of publication, but it's rather difficult to have already atomic resolution with electrical characterization. Okay, I show just one example with topography, which is already very difficult. But for electrical characterization, we will have resolutions which are in order of tip apex. So, for example, 5, 10 nanometers, etc. So we will not have access to the single atom.
Okay, thank you. Other questions in the room or through the chat? No, we don't have any in the room. Any other questions? No, so I think that was clear enough. Anyway, if you have any other questions, you can contact Lukasz. I forgot to say that he's from CEA-Leti, but you would saw in the presentation and at the end. So thank you very much. Before applauding him again, let me introduce the MIDI Minatech by Giant that we will have next week, Friday the 2nd of June. It will be given by Myrtille Gardet and Guy Chatagnier from the Grenoble Academia, and the title would be quite intriguing: The Attractiveness of the Trades and the Needs of Companies, a lightning given by the National Education, or in French, l'attractivité des métiers et des besoins d'entreprise, un éclairage donné par l'éducation nationale. So I want you here next week to June for same place, same time. Thank you very much, Lukasz, and thank you all for being here. Thank you.
Thank you.